Hey friends, welcome. Today we are going to discuss kinetics of electrode reactions and that are famously known as Butler Volmer equation. And from Butler Volmer equation, we are going to modify the Butler Volmer equation to get Tafel equation. There are basically 4 to 5 reactions that we assume that they are taking place. First, it may be the diffusion of the reactant to the electrode, then absorption of the reactant on the electrode, then the transfer of electron to or from the adsorbed reactant species, and then desorption of the product from the electrode and the diffusion of the product away from the surface of the electrode. So these are some of the processes during the kinetics of electrode reaction. All these processes, suppose again we consider a general example of conversion of any metal ion, that is Mn plus will take up n number of electrons and it is converted into again our solid metal. So suppose this is the general reaction that we are looking at, where Mn plus is our metal ion and it takes n amount of electrons and it is converted into our metal solid. Then according to Ehring's activated complex theory, the rate constant for a chemical reaction, that is the rate constant K for any chemical reaction, is given by B exponential of minus delta G star upon RT. So this is our rate constant, where delta G star is the Gibbs free energy of activation, B is any constant, R is our real gas constant, and T is the temperature of the system at absolute scale. For any metal M to convert it into the metal ion, or any metal ion taking up an electron and to convert back into the metal, it requires this much amount of energy. And if we want to show it by the activation energy diagram, then we can represent that. Suppose this is our any electrode surface and this is the distance, okay, along x-axis, and this is our electrode. So suppose over here I can write it as x0, which is our outer Helmholtz plane over here. So the minimum amount of energy that will be required to cross this energy barrier will be equal to delta G star. Okay, so delta G star is the minimum amount of energy required to overcome the energy barrier. And when we are moving from the electrode to the electrolyte, this will be our anodic process, and when we are moving back from the electrolyte to electrode, so this will be our cathodic, because electrode will lose electron and it will be converted into ion. And over here, so this is the length of our electrical double layer, and the actual path of the formation of the metal ion and again formation back of the metal is not known, but it is believed that the electrical double layer will follow our Helmholtz-Perrin model. Okay, so as we are considering that our electrical double layer is following Helmholtz-Perrin model, there will be a linear decrease in the potential as we move from the electrode to the outer Helmholtz plane or to the distance x0, okay, where our reactant molecule is located. So suppose over here we have M, that is solid, and over here we will have Mn plus. So metal will lose electron and it will be converted into Mn plus, and this will take up the electron and it will form again metal. Suppose if we are considering that transfer of a single electron is taking place, and suppose it is the rate determining step, that is one transfer or one metal is converting into a metal ion and again metal ion is converting back into the metal. And if we are considering that only a single electron transfer is taking place, okay, then that transfer of electron is the rate determining step. Suppose if we consider that C0 and Cr are the concentrations of oxidized and the reduced form of the species respectively outside the double layers, the rates of the cathodic and the anodic processes will be given by the rates for cathodic and anodic process will be given by Kc into C0, and for anodic process it will be Ka into CR. So this will be their rates, where Kc and Ka are the rate constants for the reduction and oxidation processes respectively. And in any process, the magnitude of the charge transfer is given by F is equal to E into Na, where F is our Faraday's constant, E is the N capital A, E is the charge, and Na is our Avogadro's number. And if we are considering that we are having 1 mole of any species, then Avogadro's number will be equal to the number of mole N. If you are taking 1 mole of any species, then this Na will be equal to N, and that will be equal to 1, and ultimately we will have F is equal to E, that is Faraday's constant will be equal to the charge. Okay, now amount of current I, that is amount of the anodic current or the amount of the cathodic current which is arising because of the transfer of electron. That is, if we are considering our anodic current, then anodic current will be due to the loss of electron and the cathodic current will be due to the gain of electron. So the anodic current, I can write it as IA, will be equal to the charge into the rate. Okay, so charge is F into, I will have Ka into CR, and similarly our cathodic current IC, it will be F into, it will be small kb into C0. Okay, so this will be because charge into rate will give us our cathodic current, and again charge into rate will give us our anodic current. And as we have seen, the net current density I is always the difference between the anodic process and the cathodic process. So I is the difference between IA minus IC. We have the value of IA, we have the value of IC. So both these values we can substitute right away in this relationship. So the net current density I can write it as F of Ka into CR minus F of Kb into C0. Okay, and again we have the expression for our rates, that is K, and that expression is from Ring's activated complex theory, that is K is equal to B e raised to minus delta star upon RT. So delta G star C subscript we will write for cathodic process, and delta G star A we write for anodic process, because the activation energy will be different for both cathodic as well as anodic processes. So our relation will become I is equal to, we'll have F into BA into CR into e raised to minus delta G star A by RT minus F into BC, it will be C over here. So we'll have BC into CO into e raised to minus delta G star C by RT. So this will be our relationship after substituting the value of the rate constant. Now when we are considering that IA is greater than IC, then obviously from this value we know if IA is greater than IC, then I will be greater than 0 and the current will be an anodic current, and if IC is greater than IA, then the current density or the net current density I will be less than 0 and the current is a cathodic current. Now we will consider that our reaction is under non-equilibrium condition. Suppose we are considering that reduction reaction is taking place. So when reduction is taking place, the metal ion will take up the electron and it will be converted into the metal solid, and the electrical work done during this process will be E into delta phi. Okay, that means when metal ion is converted into metal by taking up an electron during our reduction process. Okay, so the amount of work done will be E is the charge and delta phi is the potential. Okay, or delta phi is the potential difference between the electrodes. So this much amount of work will be done. Now under non-equilibrium condition, when we see this particular diagram, then there is a change in this particular energy diagram, and the new activation energy diagram, which will be the result of non-equilibrium condition, will be in this particular manner. That is, this will be the new equilibrium diagram which is under non-equilibrium condition, and this much amount, and so for cathodic process this much amount of more work will be required to transfer the electron to the metal, and this much amount of less work will be required for the transfer of any metal to the metal ion. Okay, so this much amount of more electrical work has to be done, and hence this amount of work is to be added with our activation energy. Okay, so earlier our activation energy was delta G star, and the amount of work done which we are getting was delta phi E. So the total amount of work done for, say, suppose cathodic process, delta G star C will be equal to delta G star plus, in place of E I can substitute F into delta phi, because earlier we've seen F was equal to E, and hence I can add delta G plus F delta phi. So this F delta phi is this increase in the work, and also the condition is that our metal ion has not taken up the electron totally and reached over here, but it is in some way in the middle, or it is in the path of the transit. So we need to introduce one more factor, that is a transfer coefficient or symmetry factor, which is represented by alpha, and this symmetry factor will tell us where we are in this path. Okay, so hence we need to add or introduce symmetry factor in this representation. So with the help of symmetry factor we will be able to know that where in this path actually we are. So our representation will be delta G star C will be equal to delta G star plus alpha F delta phi, where alpha is our transfer coefficient or symmetry factor, and generally the value of alpha, it lies between 0 to 1. The value of alpha lies between 0 to 1. So for cathodic process this much amount of more work is to be done, whereas for anodic process this much amount of less work has to be performed. Okay, our value of G star C will be this much, and similarly the value of delta G star A will be equal to delta G star minus 1 minus alpha into F into delta phi. This will be the amount of activation energy required for our anodic process, and this will be the amount of the activation energy required for the cathodic process under non-equilibrium condition. So the value of delta G star A and delta G star C we will be substituting in this particular relationship. We will get I is equal to F into BA into CR. So over here we have minus delta G star A, so this will become minus delta G star, and this will become plus, and I can directly separate both of them. So we will have e to the power minus delta G star upon RT into e to the power 1 minus alpha F delta phi upon RT minus FBC C0 e raised to minus delta G star by RT into e raised to minus alpha F delta phi by RT. So this will be the representation. Now from the last lecture we know that the over potential neta is potential difference under non-equilibrium condition minus the potential difference observed potential minus equilibrium potential is our over potential. So over here we have the value of delta phi, which is the value of the observed potential. So I can rearrange this term and then I will substitute the value of delta phi in above representation, and I will solve it individually by for IA and for. So the value of anodic current density IA can be written as F into BA into CR into e to the power. This will remain as such, so it will be minus delta G star upon RT. Then we will have e raised to, and again we rearrange this representation in the form that is delta phi is equal to neta plus delta phi EQ. Okay, in place of delta phi I can write neta plus delta phi EQ, and again I will separate out the individual terms, so the relation that we will be having is 1 minus alpha f delta phi eq by rt into e raised to 1 minus alpha f neta by rt. So this will be the relationship, and when we examine all these terms, then this term, because delta g star is our activation energy under equilibrium condition, this is our equilibrium potential, and this is our rate constant, and other are also under equilibrium condition. So all these terms which I have kept in this bracket will constitute the anodic current under equilibrium condition. So all the 5 terms I can write together in the form of IAEQ, which is our anodic current under equilibrium condition, and into I am left with e raised to 1 minus alpha neta f by rt. Okay, and similarly for cathodic current IC, again I can substitute over here. In place of delta phi, I will substitute neta and delta phi eq. So I am left with, or I will have IC eq into e raised to minus alpha neta f by rt. So this is what I am left with. We know that under equilibrium condition, our anodic current density is equal to our cathodic current density, and that is equal to the exchange current density I0. So this is our cathodic current density under equilibrium, this is our anodic current density under equilibrium. So both these current densities can be equated or can be written equal to the exchange current density I0, and further the current density I will be equal to, as we know, it is IA minus IC, and that I can write it equal to I0, or I can take I0 common out from both this, and hence I can write I0 into e raised to 1 minus alpha neta f by rt minus e raised to minus alpha neta f by rt. So this representation of the net current in terms of the overpotential is known as Butler Volmer equation. And further, in order to get the Tafel equation, we will examine the exponents of this particular representation. Okay, and this exponent or exponential series, we know that suppose if we are having e raised to x, then exponential series will be x plus 1 plus x square by 2 factorial plus x cube by 3 factorial plus and so on. So this will be the exponential series, and when we are considering that our overpotential is very very small, then the value of neta f by rt is very very smaller than 1, and hence the square, cube and the higher terms can be neglected, and we are only left with the first 2 terms. So the representation, or this representation, we can write it as I0 into 1 plus 1 minus alpha into neta f by rt minus 1 minus alpha neta f by rt. Okay, and further when we simplify this relation, we will have I is equal to I0 into 1 plus, I can simplify this, so I will have neta f by rt minus alpha neta f by rt minus 1 plus alpha neta f by rt. So we can cancel both these terms out, and 1 also will be cancelled out, and we are left with I is equal to I0 into neta f by rt. So from this relation we can say that the current density is directly proportional to the over voltage. Okay, so when over potential is a very small over potential, conversely if we are having that when the over potential or when the value of neta is very large, so this neta is small when we are having non-polarizable electrodes. Okay, so wherein the value of over potential is very small, but when we are having a polarizable electrodes, then in case of polarizable electrodes the value of over potential is large, and suppose when the value of over potential is large and positive, then under such cases the second term of our this particular representation. So when neta is large and positive, then e to the power negative value or e to the power minus of something will be a very small value. Okay, and when this value is very small value, we can neglect this particular or the second term from this particular relationship, and hence we will have I will be equal to I0 into e to the power 1 minus alpha neta f by rt. So this will be the relationship, and when we take logarithm on both hand side, then we will have ln of I is equal to ln of I0 plus 1 minus alpha neta f by rt, and this relation is known as Tafel equation. So this condition is when neta is very large and positive. Under such circumstances, the current will be the anodic current, and when we consider that the value of neta, it is very large and negative. So when we are considering value of neta as very large and negative, then in this representation over here for negative value, this will become positive and this term will be negative, and hence the current will be the cathodic current. So the value of the first term in this particular relationship will be very smaller as compared to the second term, and this can be neglected, and so we are left with only the second term, and hence we will have I will be equal to I0, or I will write minus ahead, I0 e raised to minus alpha neta f by rt. So we are only left with this particular terms. So first we can take minus on both hand side. So we will have minus of I is equal to I0 e raised to minus alpha neta f by rt, and further we will take logarithm. So we will have ln of minus of I is equal to ln of I0 minus alpha neta f by rt. So this will be the relationship when the power potential is large and negative, and essentially the current will be the cathodic current, and this relation is also known as Tafel equation. So both these relationships are Tafel equations. Okay, and when we plot a graph of the current density I versus the over potential neta, okay, in Butler Volmer equation, that is for this particular representation, when we plot a graph of I versus over potential, then you can see in this diagram we will get a diagram of this particular manner. Here we have considered two markings. So one which is going along the current density I, it is the case A, where there is high exchange current density, wherein our electrodes are polarizable electrodes. In second case you can see there is B, so which is moving across the over potential value, and this is the case where the over potential is very high and the current density is very low. So this is the case seen when we are using the polarizable electrodes. So in case of polarizable electrodes, the over potential will be very high, whereas in case of the non-polarizable electrodes, the exchange density or the current exchange density will be very high. Okay, so this results that are obtained from Butler Volmer equation. Hope the Butler Volmer equation as well as both the Tafel equations are clear. Thank you very much.